Hello, Eastern Scholars, and welcome back to Sharp Shorts. This will be the final discussion we have on how to name chemical compounds. And really everything we've done to this point are things that follow the rules of ionic naming, even though we saw with acids that while they're covalent type compounds, they do follow similar rules. We're going to do the same thing here, but let's remind you, as it says here, what covalent bonds are. Now this says it's the second major type of atomic bonding when they share electrons. Second just means it's the second we're talking about. Covalent compounds far exceed ionic compounds on our Earth because you can do more when you're sharing electrons. Anyhow, let's look at this first before we talk about that. Here we have water. Oxygen is denoted by the different circles here, has 6 valence electrons. That fits with what we see on the periodic table. Hydrogen has 1 valence electron, as seen by the X's here, and fits with what we know from the periodic table. What they can do then is overlap their valence shells and share electrons. Oxygen, of course, would like to have 8 electrons in its outer shell for that stability. That gives it stability that simulates a noble gas. Hydrogen is, because of its size, very small, only actually needs 2 so that it can simulate helium in the stability of that noble gas. But they're sharing electrons. Now, if I were to calculate the electronegativity difference between hydrogen and oxygen, it is less than 1.7. But remember, the water is right close to that border, so while it's technically covalent, it has a lot of ionic properties. But anyhow, it is covalent compound. But let's point this out. They're sharing electrons, and this commonly occurs when 2 nonmetals bond together. So I recognize these compounds because they begin with carbon or silicon, or they have 2 nonmetals together. Because anions, if they were to form anions as nonmetals do, they wouldn't ionically bond because 2 negatives would repel each other. And to finish the thought on covalent bonding far exceeds, it does that because one of carbon. Carbon only covalently bonds, and it's the basis of all living things and organic material on the Earth. With ionic compounds, you're really limited on the size they can make because you're limited by that neutral compound. Ions really only form charges of plus or minus 1, 2, 3. And then, of course, they balance each other by neutralizing each other's charge, so you can only have so much electrostatic interaction. Even some of the transition metals don't get that high. Most of them are 2, 3, 4, 1, 2, 3, 4 in charge, so they don't get that high. With covalent compounds sharing, especially with carbons where you can make these big chains and stuff, as all these carbons share and make a backbone and then share with other compounds, you can make extremely large complexes. We could spend our whole year just doing organic chemistry naming. We're going to limit ourselves here to binary covalent, or what are called binary molecular compounds. You use the term molecule when you're talking about things that are covalently shared. Covalent compounds share electrons. There isn't any ion formation, so the naming is the same as binary ionic. And that's why we're going to talk about this and not really get into the whole organic chemistry carbon naming stuff, because that's just such a huge part of naming that it would take a lot of time that we don't really need to spend. But the binary ionic similarity to binary covalent is the fact that you have 2 elements. The difference is you don't have those ions to balance out how many atoms are attached. Again, the ionic charges on a binary ionic cancel each other out. You know how many atoms stick together. You don't know how many atoms stick together in a binary molecular compound. And so you need to have some method in naming different than what you had with binary ionic to name them. And just as an example, I'll look at here are 2 compounds, binary compounds that have carbon and oxygen. So I follow the same normal naming, carbon, oxide, changing the ending to I to E, but notice they are not the same compound, even though they have the same name. Here, nitrogen oxide. Okay, So the binary ionic naming is the same. I name the first one, I name the second one, and I use the ID ending. Okay. What is different though is I have to have some way of indicating for these compounds how many atoms of each are being shared. Here I have one nitrogen with two oxygens. Here I have one carbon with one oxygen. Here I have one carbon with two oxygens. This is where you start using prefixes that denote the number of how many you're sharing. And on your cheat sheet you have an organic prefix naming box. Okay. So what I would do then is I would say, well, that's one nitrogen, and technically then I would take the term mono, which is the word for one, and let me help get my pen working a little better, and mono. The one exception to the rule is on the very first element I never have to use that term. Okay. So while I would say mono with the first term, I actually don't have to. I would have to use every other prefix, but I never have to say mono on the first one. On the second element, I always have to use the prefix, whether it's mono, di, tri, whatever. This is two oxygens, so this is actually nitrogen dioxide. Okay. I wouldn't count you wrong initially if you said mononitrogen dioxide, but I would indicate in the beginning of our unit to not say mono. And then by the time we got to the test, I would expect that you understand that. Okay. Here again, I have one carbon, one oxygen. I could say monocarbon, but I don't have to. But I would say monooxide, or just I don't have to put both O's together. That's actually carbon monoxide. Here again, one carbon. I don't have to use mono at the beginning. I do have to use every prefix on the second. This is carbon dioxide. Okay. So the key to these are they begin with carbon or silicon, or they have two nonmetals, anions, bonded together. Formula-wise, it tells you everything you got. Here is carbon, so I write a C. There is no charges here, so I don't have to worry about that because they are covalent compounds. Chloride means chlorine. Okay. So I write that. There's no prefix here, so that means I only had one carbon. There's a tetra here, so that means I had 4. So CCl4 is the formula for carbon tetrachloride. Okay. Here I have silicon, and it tells me it's trisilicon, because again, I have to use the prefixes. The only time I can drop the prefix on the very first one is if it's mono. And here is hexafluoride. Fluoride is F. Hexa means 6. So that's all it is for binary molecular or binary covalent compounds. Now the last thing I'm going to talk about is this. So now we've talked about binary molecular, binary molecular, binary ionic, ternary molecular, transition metals, acids, bases. Your most important of your job is to be able to distinguish all those. So you need to come up with some sort of a pattern. Here's a guide that I use that I think you could use and get used to. And just look at the very first element, what would be the cation for most of these, because most everything we did was inorganic ionic naming. And ask yourself a few questions. Look at that first element. Is it hydrogen? If it is, then you know it's an acid, and you go through your acid naming rules of first name it as an ionic compound, and then use the ending to switch it into its acid name. If your answer to that question is no, then look at that cation and say, is the cation a transition metal? Something in that D block area, or maybe scooting down to the lower levels of that P block. You can look in on your cheat sheet on the box that says metals that gives you the charges and stuff. If that answer is yes, then you know when you write the wording out that you need to indicate the charge of that cation and use the Roman numerals. If not, then the next question to ask yourself, as we just learned, is the first element carbon, silicon, or are both the elements anions, nonmetals? Then you know that it's binary, covalent, or molecular and needs prefixes. And really, this shouldn't say cation, it should say the first element, because remember, the key to covalent is there is not an ionic charge. And that's an error that folks often do trying to figure that out, is they try and put a charge on carbon or any of these negative anions and put them together, and you can't do that. Okay? So those are specialties. If you ask yourself those three questions and you come down to no to any of them, it just means that what you're looking at is a normal run-of-the-mill binary ionic or polyatomic ternary compound. And if it's three or more, then just look at your polyatomic sheet and name it as normal. And if it's two, know that it has an ID ending and that it's two elements put together. Anyhow, some use of this while you're looking at that, because everybody can name stuff if you're told this is binary or this is ternary or what it is. It's can you recognize the compound and become very proficient in that. Anyhow, that was where you need to spend a lot of your attention, is can I distinguish each of them if I'm not told what they are. Anyhow, practice on and scholar up Eastview.